Eu fui acreditando que chegaria ao céu e te aconselhando, sinto algemas presas em meus pés. Quando vi já era fim de tarde, muito tarde. Outro dia eu volto e outra vez eu vou lhe inspirar. Eu só queria estar aí.
After elaborating the requirements and making the first design considerations, as well as the first simulations of the rocket based on our experience in previous designs, we can start designing the main parts of the rocket using CAD software CATIA. For example, this one is a part of our engine, and after making all these parts, we can start assembling them into smaller groups, such as this one, which is our motor assembly along with every single screw and also the fins attached to it. And after finishing these local assemblies, we can then join them and make the final rocket assembly. This assembly can then be used to make finer simulations with proper mass and inertial measurements, the final geometry of the rocket, and we can also use it to plan manufacturing and integration procedures. And then after that, of course, the first iteration won't be perfect, so we can then engage in many kind of feedback loops with the other subsystems where we can refine our design and go through all these steps multiple times until we can get the performance, apogee, and the payload capabilities we need. And then the final part of this process, after every single design has been revised and every piece is approved for manufacturing, we make the technical drawings that will be sent to any contractor the team has, or it can also be used internally. Some of the parts, specifically 3D printed parts and some laminated tubes, are made here internally. This way we can make sure that the rocket itself is built under our standards.
Hello, my name is Isabella Gomes and I'm this year's Propulsion lead, and I'll be presenting the motor project, the RDS X-Lite Plus. It was based on a last year's project and we tried to optimize as much as possible while still maintaining the same genetic code. It has the same propellant as before, the HTBB, and it has a similar design, but it was optimized. Due to the pandemic, we didn't have the chance to perform static and hydrostatic tests, but we intend to do both because we also intend to do a launch in the end of this year, or when the pandemic wears off. The specifics of the motor are: it has a propellant mass of 4.5 kilograms, a burn time of 6 seconds, a max thrust of 2,157 newtons, and an average thrust of 1,647 newtons, and an ISP of 229 seconds. We are very happy with the result and very excited for the testing for the launch. Now we're going to our lab to look at our motor and to compare it with the last year's project. So this is our new motor, our little baby, and this one is the motor we used on the last competition before coronavirus in 2019. As you can see, the difference is quite notable. This one is roughly 15 kilos heavier. This one is still made of steel because due to the pandemic in Brazil, we could not manufacture it. But the aluminum is the same design, and our simulations show that it's completely safe to test with the steel motor.
Hello, I'm the head of the flight mechanics subsystem, and this is our simulator. This is our RDX rocket in all of its glory.
Wait, no, boss, that's not our simulator. This is our 2 degree of freedom simulator in MATLAB. We use it in the initial stages of development to generate estimates of relevant parameters, such as the apogee and the maximum Mach number for our rocket during our flight, based on preliminary designs given to us by our team.
On the later stages of our project, we have access to further aerodynamical data, such as the aerodynamic moment coefficients and the full mass distribution of the rocket. This enables us to perform a 6-degree of freedom analysis on our flight, providing much greater accuracy than the previous simulation showed.
In order to validate the data we gathered from our own student-made simulators, we utilized the Open Rocket software. This is a commercially available simulator designed specifically for rocket modeling. Furthermore, all of the data shown in our report actually comes from this software.
After executing the simulation, we are ready to gather relevant data. In addition to data required by the other subsystems, such as the maximum Mach number and the maximum acceleration, we must verify competition requirements, such as the apogee and stability on rail departure. The predicted flight apogee falls very near to the target apogee of 10,000 feet or 3,000 meters above ground level. Now, concerning stability on rail departure, the team's rocket does not reach the recommended 100 feet per second on rail exit. Therefore, we needed to ensure the stability of the rocket through a dynamic stability analysis. Here on these graphs we can see the angle of attack and the angle of slip, both with respect to time. You can see the heavy dampening on these angles and the small amplitude of the oscillations, which ensure the stability of the rocket. Here on the bottom we can see the evolution of the roll angle with respect to time, and it wraps around 0 and 360 degrees several times due to the rocket's rolling motion, which actually contributes to stability. And now back to our real simulator.
So this is the electronic system of our team, and the main objective of the electro project is to acquire and transmit the critical data, or as we can say, to acquire GPS and inertial sensors, reading and transmit the latitude, longitude, and altitude of the rocket, while also storing the data as a backup for further analysis. So our subsystem assembly, it's located on the nose cone, and it's composed by 3 boards. And here we have the first one. Let's take a closer look.
So here we have the assembly of our main board. It's centered around an Arduino Dual board, and it fulfills all our system's primary goals. As we can see here, we have a GPS PON7Qui module, which is our main GPS module, and its data, it is transmitted to an XB, which is mounted on the Arduino with this shield. We also have some sensors here. The first one, this one's a magnetometer, which we use to locate the rocket's orientation relative to Earth's magnetic field. And this one is a 7 degrees of freedom IMU, and it comes with a temperature built-in sensor, from which we also get readings from. This one is a backup battery. It's a 3-volt lithium battery, which we use as a backup voltage for the GPS in case anything goes wrong with the system. The GPS doesn't lose any signal and can keep transmitting as if nothing happened. Here we have the SD card module, which we store all the data that the sensors read for later analysis. And as a secondary solution, we have a feather rate GPS tracker as a reduced tracking solution. We usually build this assembly on a printed circuit board, but due to the pandemic situation we couldn't get one, so we had to make one with a breadboard. Here we are supplying it directly with the battery, just for demonstration purpose. On the real field, we use one of those, which is a board we also make with a diode, so we can plug an external battery to prevent the internal battery from draining out before we launch the rocket. The diode is to not allow the internal battery to charge the external battery, so it's a one-way only power entry. And as soon as we unplug the external battery, it switches automatically to internal power. As a matter of redundancy, we utilize two assemblies like this one, so we utilize two main boards with all of its components.
By using high power XV 200 milliwatts with a rubber duck 3 dBi antenna and receiving with a 5 dBi cloverleaf antenna and XB receive of minus 110 dBm at 10 kilobit sensitive, it's possible to retrieve the signal from the transmit at distance as far as 50 kilometers if necessary. Therefore, even considering the noise cone and environment noise, we expect to have a stable and smooth data transmission.
So at this assembly, we conduct three types of tests. The first one, which is a short range test, which we do just like that one we just showed. We just check if this thing is sending the package correctly and the other end is receiving it at really short range, like at maximum 100 meters or something like that, with a direct line of sight. We do also a long range test, which we try to push it up to 3 kilometers on the same way. And we do a battery life test.
Hello everyone, I will briefly explain how our recovery system works. Basically, it is composed of three parts: the drogue tube, the avionics tube, and the main parachute tube. Starting by the avionics, we have in the tube's interior a metal plane used as a spine connected to two bulkheads. In one of the spine's face, we have two batteries tied by zip ties and PLA boxes screwed in the plate. On the other face, we have two mini altimeters connected to the batteries by cables that pass through the spine. In the bulkheads, we have two gunpowder containers sealed with cotton and masking tape. In each container, there is a skip connected to the altimeters through the bulkhead. Furthermore, we have a micro switch for each altimeter installed in PLA boxes screwed in one of the bulkheads. Those micro switches ensure that the altimeters keep inactive while the rocket does not launch. With this, just before the flight, we pull the remove before flight pins so we can activate the altimeters. The parachutes are localized in the drogue and main tubes, are folded inside an anti-flame bag and covered by a thermal blanket to keep the parachutes from burning during the explosive activation. It is worth noticing that both parachutes are connected to the rocket structure through shock cords, carabiners, and swivels. During the flight, the altimeters are able to read the barometric pressure and determine the rocket's altitude and its consequent velocity. This way, when the rocket reaches its apogee, both altimeters, for redundancy, activate with some time delay between one another the explosive containers attached to the bulkhead closer to the drogue parachute, splitting the rocket into two parts so that the parachute can open. Then the rocket is lowered down until it reaches the terminal velocity of 30 meters per second. When the rocket reaches approximately 700 feet, both altimeters activate, with some time delay between one another, the remaining explosives containers in the bulkhead closer to the main parachute, once again splitting the rocket in more parts so the main can open. The main parachute opening in this altitude allows the rocket to reach a terminal velocity of 6 meters per second and land in the ground with safety. Besides all this process, our team needs to ensure that no part of the rocket collides with each other during the opening of the parachutes. To accomplish this, we consider the following stages of the flight: the splitting during the drogue activation, the drogue opening, the split during the main activation, and the main opening. For each one of these stages, we scale the respective shock cords so we can be sure that parts won't collide with each other. Thank you for watching.